Alrighty, guys, we are back. Today we're going to be doing inscribed angles. It's already lesson number 13. Wow, can't believe we already did 13 lessons of remote learning, but here we are. All right, we've actually done quite a lot of circle theorems already. Right, we've done the central angle theorem, we've done theorems involving chords, we've done the tangent line theorems. Right, and today we're going to be doing inscribed angle theorems. So I would highly recommend probably just making a new notability file where we write down all the theorems that we have so far, because it can be quite a lot to keep track of, and especially with circles, which are probably pretty new for all of you. So might be a good idea to do that because we actually still have quite a bit of theorems remaining after this. All right, so today we're going to be doing inscribed angle theorem, and yes, we are going to be proving this theorem later. Hooray! All right, but before we get to that, well, we have to define what an inscribed angle is. So we already know what a central angle is. That's an angle where the vertex is at the center of the circle, right? And it's made up of two radii. So where is an inscribed angle going to be? Well, think about the word inscribed. When something is inscribed in the shape, let's say I inscribed a square in the circle, right? Each of the vertices of the square is going to be on the circle, right? Same thing if I inscribed a triangle, right? Or a pentagon or anything else. So an inscribed angle is going to behave the same way. An inscribed angle is going to be an angle where the vertex of that angle is on the circle. So for example, this here is an inscribed angle. Right, so definition. Let's write this down like so. An angle whose vertex is on the circle and formed by, so we know a central angle is formed by two radii. An inscribed angle is going to be formed by two of these guys, what we call those line segments. Very good, formed by two chords. Right, so a chord can include a diameter, for example, if that's the center of the circle, right? This here, that would also be an inscribed angle, right? Those are two chords. A diameter can be considered a chord, right? A central angle is never an inscribed angle, right? It's not inscribed within the circle, right? Its vertex is at the center, not on the circle. Right, so what do we know about this inscribed angle? What properties does it have? So we're going to do this inscribed angle lab and see if we can see a relationship or any relationships. So I did finally download the TI Inspire software and get it registered. So hopefully this will work when I share that screen. So I gotta do this. All right, so hopefully you can see my calculator now. I will check after this recording, and hopefully you guys can see this shared screen. So I am on a geometry page, and step one of this lab says construct a circle. So let's go to menu. Right, you better all be doing this, guys. You can pause the video, you have plenty of time. So we're going to go to shapes, and we're going to make this circle. All right. If you don't have your calculator out, make sure you go grab it. I'm serious, it's a good lab. Next, menu. We're going to construct next an inscribed angle and measure this inscribed angle. So inscribed angle is made up of two chords, which are line segments. So I'm going to go to my line segment command, and let's draw in that inscribed angle. So menu, measurement, let's measure that angle. 1, 2, 3 clicks will do it. Wow, look at that. Got 50 degrees. All right, next we're going to measure in degrees the arc that's intercepted by the inscribed angle. Unfortunately, these calculators cannot measure these arcs in degrees. All it can do is measure the arc length. So let's go ahead and measure that arc length. All right, but before we can do that, we actually need to draw in an arc. Your calculator does not recognize this as an arc yet. So first go to Menu, Points and Lines, and go to Circle Arc. So we need 3 points to define an arc on your calculator. So we're going to click at this endpoint first. We're going to click on the interior of the angle on the circle, any point in between, and we're going to click the endpoint, and there we go. We drew the arc from there to there. So next, I'm going to measure that arc length. So I'm going to go Measurement Length. And right now, if I hover over the circle, right, you'll see that's going to be measuring the circumference of the entire circle. I'm actually going to be using this number in a second. And if you hit Tab over here above the arc, right, the length of that arc is 10.3 centimeters. So I wanted the measurement of this arc in degrees. So let's think about how we can get that measurement in degrees using these two numbers, using this arc length and the entire circumference or the perimeter of the circle. So we actually did this in our first lab. That was when I gave you bad instructions. So hopefully this time we can all do it. We're going to go to Menu, Text, and the calculation we're going to do to get the arc measurement in degrees is A over B times 360. All right, think about what A is going to be and what B is going to be. So we're going to go Menu, Actions, Calculate. I'm going to calculate this expression where A is equal to 10.3. Select B. B is going to be 37. And I'm going to get 99.9. I'm going to put that there. All right, so that is the measurement of this arc right here. So how I got that, again, is I measured the arc length. I divided it by the circumference. Right, this, in essence, gives me the fraction of this arc length as a ratio out of the entire circle. Right, so it's like what fraction this arc is of the circle. So if we multiply that by 360 degrees, that's going to give me the measurement in degrees. And so if I adjust these numbers, try to round it, right? But if I go, for example, why is it not working out exactly? Come on. If I go to, there we go. I go to 36.1 degrees here. The measure of this arc in degrees is 72.2. Do you guys see a relationship, right? I'll add 40 exactly for a second. You see a relationship between 40.3 and 80.6, right? 70.1 and 140, right? Ignore the rounding, but hopefully you're seeing that the measurement of this arc is twice the measure of the inscribed angle, or the inscribed angle is half the measure of the arc that it intercepts, right? We can say this inscribed angle intercepts this arc. Another word for intercepts might be the word subtends, right? We'll write that down in a second, but those mean the same thing, right? If you move this point around and you move it past this middle point, which we use to define the arc, right? We're going to be measuring the major arc now, so it gets kind of messed up. So make sure that point, you can move it back into the middle, right? And then it'll be measuring that minor arc. So again, inscribed angle, 11.2. The subtended or intercepted arc is twice the measure, or the inscribed angle is half the measure of the intercepted arc. Very cool. And of course, as always, that was not a proof, however. So let's prove it. So let me get back to my iPad. Screen mirroring, zoom. All right. So let's first write down the inscribed angle theorem. This theorem says the measure of an inscribed angle is equal to half the measure of its intercepted arc. Right, and another word for intercepted is, you'll see the word subtended. Subtended arc. Right, and this really just means the arc that's formed by this inscribed angle. And so it's just some fancy vocab, but that's all it means. All right. So to prove this theorem, we actually need to consider 3 cases. And they're all very similar, so we're just going to write out a formal proof for the first case, and then we'll just analyze the other 2 cases. All right, so let's take a look at case 1. So this first case is when the inscribed angle has one chord that is a diameter. So let's draw a picture. Here is a circle, and here is the center of the circle. Let's call this circle O. So if I draw my inscribed angle, one chord of this inscribed angle is going to be also a diameter. So I'm going to name this angle A, B, C. All right, so angle ABC is an inscribed angle. And again, we're trying to prove that the measure of that inscribed angle is equal to half the measure of its intercepted arc. So let's think about what our given is going to be. Let's say given inscribed angle ABC in circle O. We're trying to prove that, well, again, are we trying to prove that this measurement here is half the measure of that arc? So we're trying to prove the measurement of angle ABC is equal to half the measure of, what was that arc? Of arc AC. Cool? So let me do a quick analysis of this, and I'm going to use some variables to make it easy. But let's suppose the measure of this arc here were x degrees, so you can call it theta, whatever you want. So we want to prove then that this measurement is 2x, or show that it's 2x, because then this would be half of that arc. So how could we do that? So we're going to need a construction, and we're going to construct what we always construct in a circle. It's going to be this radius we're going to construct. So think about what kind of triangle we have once we draw in that radius. Well, isn't it an isosceles triangle? Because those are both radii. So we know in an isosceles triangle, right, the base angles are congruent, or we can say in any triangle, angles opposite congruent sides are also congruent. So that would mean this here would also have a measure of angle x. And what would the measure of this angle be? Well, that is an exterior angle, which is equal to the sum of the 2 remote or non-adjacent interior angles, which means this angle would be equal to x plus x, or 2x degrees. And hey, look, angle AOC, that is a central angle. And we know central angle intercepts an arc that is equal in measure. So this would also be 2x degrees. And we have shown that inscribed angle is half of that guy over there. So that's going to be our proof. But let's write this one out formally. If you want, you can pause the video and try it yourself now. Right, but that is what we started with. And I'm just going to write down the statements. And let's take this one step at a time. All right, so step 1, given. All right, copy and paste. Again, I'm only writing down the statements, so make sure you're writing down, right, given over there. Write down the reasons. All right, step 2. Well, like we said, as always, we're going to construct a radius for a lot of these proofs. So let's construct radius AO. Construct radius AO. And we should all know the reason is because between any 2 points, only one line segment can be drawn. Next, we know those 2 radii are congruent. Okay, what is that? AO and BO. AO is congruent to BO because all radii in the same circle are congruent. Now we can say angle ABO is congruent to angle BAO. I'm going to call those angles 1 and 2 to keep it simple. So angle 1 is, well, actually, I'm not going to say the angles are congruent. I'm going to say the angles are equal in measure. So the measurement of angle 1 is equal to the measure of angle 2. And the reason for that is angles opposite congruent sides in a triangle are equal in measure. All right, step 5. Well, next we said that AOC was an exterior angle of this triangle. So if I call this angle 3, I know that's going to be equal to the sum of measure of angle 1 and angle 2. So the measurement of angle 3 equals the measure of angle 1 plus the measure of angle 2. Right? And the reason for that is in a triangle, an exterior angle is equal to the sum of the 2 non-adjacent interior angles. All right, step 6. What next? What was next? We know that AOC is a central angle, which means the measurement of this arc is also equal to the measurement of angle 3. So next step, the measurement of angle 3 is equal to the measurement of arc AC. Measurement of arc AC. Right, and this one I will write down the steps because that is a relatively new theorem. Right, the reason for that is the degree measure. The degree measure of an arc is equal to the measure of the central angle which intercepts the arc. And I think I wrote it kind of wordy, but yeah, just something with that idea. I'm sure you can shorten it down if you tried. Right, but that arc is going to equal the measure of the central angle which intercepts that arc. All right, so we're still trying to show that this here is twice as big as that measure, or this angle is half the measure of angle AC. So let's relate arc AC, the measure of arc AC, to the measure of angle 1. So measure of arc AC is equal to the measure of angle 3. So first of all, I'm going to do a substitution. The measure of arc AC is equal to the measure of angle 1 plus the measure of angle 2. Right, I just took this and subbed it in for the measure of angle 3. I'm going to do another substitution. I'm going to say the measure of arc AC is equal to the measure of angle 1 plus, well, the measure of angle 2 was equal to the measure of angle 1 from that step. Right, so I'm just going to say measure of angle 1 plus measure of angle 1, which is 2 times the measurement of angle 1. Right, so both of those steps is just substitution property. And finally, if I divide both sides by 2, I get that the measure of angle 1 is equal to half the measure of angle AC. Not angle AC, arc AC. So isn't that what we set out to prove, right? Angle 1 was angle ABC, right? So measurement of angle 1 or measurement of angle ABC is half the measure of the arc. So I'm actually going to replace angle 1 with measurement of angle ABC, right? Just so it looks exactly like what we were trying to prove from the start. And there we go. So last step, all I did is divide both sides by 2, so that's just division. Cool? All right, so that's the first case, and we do need to consider 3 different cases because all the cases are proved slightly differently. So that's our first case where the inscribed angle has one chord that is a diameter. All right, case number 2. This is going to be the case where, let's see, the center of the circle is in the interior of the inscribed angle. All right, so in the first case, the center was on the inscribed angle, right, because one of the chords was a diameter. So in case 2, the center is going to be inside the inscribed angle, something like this. And again, we're trying to show that the measurement of this chord is twice the measure of the inscribed angle, or the inscribed angle is half the measurement of this chord in degrees. So we're not going to go through a full proof. I'm just going to talk through it. The main thing is we're going to draw in this diameter here. Let's pick a different color. All right, once we draw in this diameter, well, let's see. Well, don't I have, I can draw 2 central angles in now, right? One like that, one like that. And let's say that this central angle had a measurement of x, and this central angle had a measurement of x. That would mean this chord here had a measurement of x, and not this chord, sorry, this arc here has a measure of x. This chord here has a measure of x. What am I doing? Let me introduce some letters to make this easy. And let's call this D. Right, so arc AD has a measure of x degrees. The measure of arc DC has a measure of x degrees. And from our first case, right, well, now we know the entire arc, sorry, has a measure of 2x degrees. So from our first case, we know that, hold on. Wrong. Sorry. So let's say that's x. Measurement of arc AD would have a measurement of x. The measurement of arc DC would have a measurement of x degrees. And now, I'm sorry, from the first case, we know that, well, this chord here, right, is also a diameter. So from our first case, we know the measurement of angle ABD is half the measure of arc AD, right? There's our inscribed angle, ABD, intercepts this arc, AD, which means this will be half of that angle measurement, half of x. Same thing for the measurement of angle DBC, right? That's also going to be half of x. And there we go. So in total, this angle here is x, which is half of this entire arc, which has a measurement of 2x degrees. So that is case 2, right? It's pretty much the same proof. We're just using what we've shown in case 1. It's a whole bunch of steps. So yeah, that's the idea behind it. And case 3, going to be super similar. Let me copy and paste this. Copy, paste, and that is when the center of the circle is in the exterior of the inscribed angle. So that's going to look like, here's my inscribed angle, and let's say here is the center of the circle. So again, we're going to be doing something super similar here. Let me actually draw this inscribed angle a little differently. Something like this, let's say. All right, so again, we're saying this angle, this tiny angle here, is half the measure of that arc. Let's call this ABC again. So what you do to prove it in this case is we're going to draw in this diameter, right, BO. Let's call this point D here. And, well, we can say, what can we say? Let's see. Well, again, from the first case, we can give this some value. let's call this, here, let's call this entire thing x. This here is going to be 2x. And actually, I'm not entirely sure of the steps, but I don't want to like fudge through it, but I'm sure you guys can figure it out. All right, it's going to be very similar to case 2, this proof. So I'm actually, well, actually, I don't want to just fudge through it because I'm not exactly sure of the steps, but why don't you guys look this one up for homework or something like that? We'll see. Hold on, let me pull it up. I have this somewhere. Give me a second. All right, case 3. All right, I'm sorry, I actually don't know where it is, so I'm just gonna leave it like that. But let's do some examples now with our inscribed angle theorem. So first example here, given the measure of arc BC is 100 degrees, that is 100, and the measure of angle B is 70 degrees. Find the measure of all 3 inscribed angles and the measures of the 3 minor arcs. So pause the video, take a minute to do this. This shouldn't be too bad. And all right, here we go. So we know if that's 70, that's an inscribed angle, which means that this arc is going to be twice that measurement, or 140 degrees. If the measure of arc BC is 100, then it's an inscribed angle. BAC is half of 100 degrees, which would make this 50 degrees. And now we can find the measure of angle BCA in 2 ways. We can do sum of the angles in a triangle out to 180, in which case we would get 60 degrees here. Or we can say in a circle, right, it adds up to 360 degrees. So 100 plus 140 is 240, and 360 minus 240 is 120 degrees. And half of 120 degrees is, again, 60 degrees. So you can do it either way. And that's what we're doing for inscribed angles. So here are a bunch of examples. I might just give you the answers for some of them, but let's do a couple of these. None of these are too bad. So find the measures of the labeled angles in each of these diagrams. All right, so angle Y, measure of angle Y here. If that's Y degrees, then this will be 2Y degrees. Doesn't help at all. So let's see, what can we get? I see an inscribed angle here at 74 degrees, which would make the measure of arc BC here twice 74, or 128 degrees. Aha, I see another inscribed angle, BDF, right, which means the measure of the arc it intercepts, which is this guy. BF is going to be 2 times 28 degrees, or 56 degrees. And if that's 56 degrees, we have now a way of finding x, because x is the inscribed angle to arc BF as well. So that means x is also 28 degrees. Right? And oh, that's actually a pretty important fact. I want to add that over here. Right? When you have some arc, there are an infinite number of inscribed angles that include those 2 endpoints. So for example, if this were, I don't know, let's say that's 60 degrees, this angle here will be 30 degrees. But if you have another inscribed angle with those 2 endpoints, like that and that, well, guess what? That's also 30 degrees, right? If I have that inscribed angle, 30 degrees, any inscribed angle involving those 2 endpoints, right? They're all intercepting the same arc. They're all going to have measurements of 30 degrees. So this angle, BDF, and this angle, BCF, are intercepting or subtending the same arc. Hence, they have the same angle measures. So if that's 28 degrees, this is also equal to 28 degrees. FD, therefore, is 56 degrees. And now we can figure out the length of CD by adding up these numbers and dividing by 2. Not dividing by 2, subtracting from 360. And good thing I checked my notes real quick because I noticed I messed up that calculation. 2 times 74 is 148, not 128. So we saw for CD, that is 204 degrees, I believe. No, not 204 degrees. What is this? 56 plus 56 is 112. 112 plus 148 is 260. All right, so this here is 100 degrees. All right, measure of CD is 100 degrees. Therefore, the measure of angle Y is 50 degrees. And we could also have just used this triangle here, right? And some of the interior angles in that triangle should be 180. There's so many ways to do this, but let's just double check that method works as well. 28 plus 28 is 56 plus 74. That's 120, that's 130, plus 50 is 180. All right, cool, cool, checks out. Letter B, we're looking for the measure of angle Y here. So that's 34 degrees. Does this mean the measure of angle BC is 2 times 34? No, you have to be very careful because this angle here is not an inscribed angle, right? Its vertex E is not on the circle. So there is a theorem for angles like these that are just floating around, but we're not there yet, so we don't know that theorem. But what I could do is I could use the 14 degrees. So that's 14 degrees, which means this is 28 degrees. And what else do we have? That's 28 degrees. That means that angle is also 14 degrees. What else can we do? Let's see. I'm actually stuck for a second here. Right. I'm just going to write stuff out that I can. I know this is 2y, which would also make BFC y degrees. Anything I can do with that? And how does this 34 degrees help us? Let's see. Figured it out. Sorry, it took me a while. All right. These two angles are interior angles of this triangle here. So if we do 14 plus 34, what is that? 48. 180 minus 48 degrees, that is 132 degrees. So it's getting kind of cluttered. I'm going to erase this 28. All right, that angle there is 132 degrees, which means the measurement of angle Y is 180 minus 132, which is 48 degrees. All right, so that's the way I see for getting Y. I'm sure there might be another way, but you just got to play around with these sometimes. It takes a while to see. All right, this one, that's 40 degrees, which means BC is 80 degrees. I'm guessing this angle there is 112, which would make this its supplement. 180 minus 112 is 68 degrees, which makes CD 100 and, well, it doesn't because that's not an inscribed angle, so be careful with that. Make sure you don't make that mistake, like I was about to. What can we do? Oh, well, we can find the measure of angle ACD now. Right, so let me just write this small, 68. That's 108. 108, and what's 180 minus 108 is 72 degrees, which will make, if I extend this guy, we got another inscribed angle here, which will make this 144 degrees. All right, what the heck am I doing? I don't know, I'm just finding angles. All right, that's 144 degrees, twice of 72. And so from there to there, that's 144. From there to there, that's 80. Wait, how the heck did I get 80 degrees there? Oh yeah, twice of 40. I'm stuck again. So we gotta think. All right, I guess I also know this is 68 degrees. And, oh, what am I doing? So simple. All right, so I'm sorry, sometimes you just gotta play around with it. But that's 80 degrees. This time I'm gonna be using a central angle, BAC, right? That central angle is the same as the measure of the arc it subtends. So that's also 80 degrees. There are supplements, so that is 68 degrees. And then we can find x using the sum of interior angles in a triangle, making that 32 degrees. Is that right? 32, 90, yep. All right. All right, next, letter D. Find a measure of angle y and x. So central angle, if that's 120, that means that's also 120, which means this here is half of 120, or 60 degrees. If that's 60, then I have a quadrilateral here, by the way, EBAC, right? EBAC is a quadrilateral, which means that that angle and that angle is going to add up to 360. So 120 minus, or 120 plus 240 is 360. Sum of interior angles in a quadrilateral is 360 degrees, so you can use that to solve for x. I believe that gives you x is 36 degrees. And now to solve for y, aha, I like this one. So x is 36 degrees. If this arc here has a measure of 120 degrees, doesn't this major arc, that entire arc, right? Well, that's going to have a measure of 240 degrees, because 120 plus 240 is 360. That's the sum of the angles in a circle. And here is the inscribed angle to this 240 degrees, making measurement of angle y 120 degrees. Right, so I'm not going to do the last two. I'll just give you the answers for those. Right, but you can see how you might need to play around, look for central or inscribed angles, and yeah. And when you're lost, like I was some of these times, just try to find whatever you can, and eventually you're going to get somewhere. All right, so just play around with these. On letter E, if you want to try this one, x is 40 degrees. And for this last one, x is going to be 30 degrees if you try it. All right, if you have any questions, let me know. Oh, there is a trick on this last one. If you want to try it yourself first, pause the video. But this is going to be an equilateral triangle, so it ends up being pretty easy once you figure out that fact, right? Because AB and AC are both radii of the same circle. All right, and again, I apologize about case 3, but I'll post something up about it once I figure out what the heck's going on there. But that's it for today. So again, I highly recommend writing down all the theorems because we have quite a few already, and we are going to be adding more. So in the meantime, stay safe, guys. I hope you guys are taking care of each other and that your families are doing well. All right. And have a nice day.